For problem number 3, we are deriving an expression for the gravitational force on a small mass as a function of r when it's moving inside of the Earth. So I am going to direct you to the universal gravitation notes, slide 27, because they walk through the proof to get the gravitational field within the center of the Earth. So I'm not going to go over that part with you. You can look at the set of notes to get that understanding, and you end up with a gravitational field of negative g, mass of the Earth, times the radial position it is within the Earth, and then the capital R is the radius of the Earth cubed. So I always use capital M to represent the bigger mass. In this case, it's the mass of the Earth. Okay, and then when we are trying to derive the force of gravity, we know that force is equal to ma. We know that the gravitational field is acceleration due to gravity. So then all we have to do is take our mass and our acceleration due to gravity above, and you've got your equation for gravity. Capital M, little r, and then radius of the Earth cubed is when r, that should be the other way around, when r is less than the radius of the Earth. For part B, it says derive an expression for the gravitational force on the small mass as a function when the mass is outside of the Earth, so when r is greater than the radius of the Earth. I want you to go to the universal gravitation lesson, slide number 15, and they have the full proof for that in there, which you guys have it in your physics equation sheet anyway. Force of gravity when r is greater than is equal to negative g m little m over radius of the Earth squared. So for part C, we've got the function for the force of gravity when it is inside the Earth, and the function for the force of gravity when it is outside of the Earth. So in this scenario, we know that there's going to be a change at r, if we call r e the radius of the Earth. For the first force of gravity, where it's less than re, we see that we've got r here. The radius of the Earth doesn't change. Everything else is constant. So this is a linear graph. It's going to go in the negative direction, and we're just going to draw a linear graph hitting some point and stopping at re because we know it's going to change. By the time we get to the radius of the Earth, we have a new function, and actually I messed up here. I need this to be squared, and I'm going to use yellow. So in this new function, the radius is now in the denominator. And since it's in the denominator, we know that as the radius increases, the force of gravity is going to approach 0. And because it's radius squared, it's going to have some sort of exponential curve to it. And it's going to look something like this. Now, at the point of change, this position down here at the very bottom would be some point where we've got GMMR, or you can call it negative, over r cubed is equal to negative GMM over r squared. So they equal each other at this point. So you could just name it. This one, I think, is the simplest form of the two. But when this r equals the radius of the Earth, obviously one of those radius values drop out, and we just have r squared in the denominator. So let me outline this graph. This should be a nice linear graph right here. And then it starts to approach 0. Okay, so for problem part D, we are trying to find the work done by the gravitational force when it's moving from the surface to the center. And from the energy unit, we know work is equal to the integration of force dr. And we are going from the radius of the Earth to the center 0. Because we're working with the center of the Earth, our gravitational force is going to be negative g big M little m r over radius of the Earth cubed. And again, big M is going to be the mass of the Earth with respect to r. But what's nice is all of this is a constant, so we can just pull all that out. And we've got the integration from the radius of the Earth to 0 of r dr. And that's easy math. That's just going to be r squared over r. So I have negative g mm over radius of the Earth cubed, r squared over r squared over 2. And then I can go from radius of the Earth to 0. So I'm going to bring the 2 out. I'm going to get negative g mm over 2 times radius of the Earth cubed from r squared from 0 to radius of the Earth. And that leaves me with 0 squared minus radius of the Earth squared. What's nice is this ends up canceling out. These two negatives turn into a positive, and we've got the radius squared cancel out with 2 of the radius cubes in the denominator. And so we end up with final answer of work equal to g mass of the Earth, mass of the object, over 2 times the radius of the Earth. And that is your final answer. Okay, so for part E, this one is a difficult problem. I did it with you guys in class, but I know that that it might have been hard to follow, so I'm going to do it again in this video. So you've got the speed of the mass, and you're also given a density. It's good to know that density is represented by rho. We'll see it a lot in the electricity and magnetism units, and it is equal to mass over volume. So I'm going to use a capital V to represent volume, and the volume of a sphere is equal to 4/3 pi r squared, pi r cubed, which is also in your physics helper, so that's good to know where to find those volumes. And then since we're trying to find speed, we can use conservation of energy, because kinetic energy will give us the speed of the object at the center of the Earth. So on the surface, compared to at the center, we do have some gravitational energy. Let's call it gravitational plus kinetic equals gravitational plus kinetic. We're going to use C for center and S for gravitational. We're going to say that at the surface of the Earth, because we are now working with universal potential energy, U is not going to be 0 on the surface. It's actually going to equal 0 at infinity. So on the surface, we're going to have some gravitational potential energy. Let's say that it starts at rest, because we won't be releasing it. It won't be moving. We will release it at the surface of the Earth. So it'll start at rest, so no kinetic energy on the surface. And then we've got gravitational at the center and kinetic energy at the center. Now, a lot of students wonder why we have gravitational at the center, and you have to keep in mind that we have a different equation for gravitational energy at the center versus gravitational energy at the surface. So the gravitational on the surface will not fully convert to kinetic energy. These guys are totally different equations. Very similar, but different. So now we've got on the surface, we've got the, actually, let's go ahead and isolate kinetic energy first. That's going to equal the gravitational on the surface minus the gravitational at the center. And then this whole thing is going to equal work done by gravity. So when we have change in energy, we have negative work done, and negative work done is equal to negative the integral of force with respect to r. And then from here we get negative integration from the radius of the Earth to 0 of g capital M little m r over radius of the Earth cubed, because we're working with the force of gravity within the center of the Earth, dr. Well, we already solved that. That we solved, let me see, right here, right? Because we did the integration of the force of gravity in the center of the Earth. And then we also got the final value right here. So I can just say that the kinetic energy at the center is going to equal gm little m over 2 radius of the Earth cubed. Oh, sorry, radius of the Earth, no cubed. And that's a 2. And from there, we know that kinetic energy is equal to 1/2 mv squared. So we've got this equation now, and we can start solving for velocity. So the 1/2s cancel out, the little masses cancel out, and v is equal to the square root of gm over radius of the Earth, which I wish we could say we're done. This is the mass of the Earth, radius of the Earth, but they did give us rho, which means that we need to figure out how to incorporate that into our equation. So if we're working with rho, we know that the mass of the Earth is equal to rho volume of the Earth, and the volume of the Earth is 4/3 pi radius of the Earth cubed. And so our velocity is equal to the square root of g rho 4/3 pi radius of the Earth cubed all over radius of the Earth. And that simplifies down to 4 g rho pi radius of the Earth squared, should be a squared, all under the square root. And then we can pull out our square values and have the square root of g rho pi. And, oh, we're missing the cubed in the denominator. And that would be your final answer.